Welcome back to the unofficial Handmade Hero Mac platform layer. My name is Ted Bendixson. I'm your host. Today what we are doing is what we always do. We are learning how to make a game engine from our bare hands with no tools, no libraries, everything from scratch in C on the Mac. And so the goal is to get you to be able to follow Casey Muratori's Handmade Hero series. The only difference is we're starting on a Mac initially for the platform layer, and then right around day 25 of his series, probably a little longer on mine because we took a bit of extra time on the days interacting with the HID library, the Human Interface Device Library. Which is, I say no libraries, but it's not really, it's as few minimal libraries as possible. We could say that. Anyway, right around day 25 or so of his series, you'll actually get into the fully cross-platform programming a game, and that's a pretty cool place to be. And from there, I would imagine you can just follow the series completely without really needing much assistance. Although I think I will do a few other videos to just kind of sort of nudge people along in the places where they're likely to get stuck. So that's the thinking. Right around this day, we are doing memory allocation in a cross-platform kind of a way. We're not allocating the memory in a cross-platform sort of a way. And as with the other episodes that kind of explain some of the cross-platform architecture, I really do recommend that you watch Casey's explanation before coming here, because really, I'm really just serving as like a facilitator here. Like my goal is just to show you the Mac way to do it, not necessarily to give you what I would call kind of the better explanation as to why we're making one particular decision or another. But there is a whole discussion about how games can manage memory and how applications can manage memory. And to be somewhat succinct, what you may have noticed if you are a professional programmer working in some kind of a business context is it's very often the case that we don't really have much of a strategy for managing memory. We may say that we have kind of a strategy, or we sort of may wave our hands about what that strategy is, or maybe we know what it is kind of and just sort of like roughly are okay with it, but we don't usually ever explicitly sit down and have that conversation about how is memory managed in this application. And if you're used to most commercial programming is usually done in a language that's a little bit higher level than, say, C. So on a Mac, that would be Objective-C or Swift. And those languages are, sort of the generic term for it would be like garbage collected. Even though I was at an interview at Facebook and I like somehow, like the interviewer asked me, well, like, how is memory managed in Objective-C? And I think I said, at the time I probably wasn't as knowledgeable as I am now. I said, it's a garbage collected environment, which is to say that we dynamically allocate memory for every time we create something. And so, this is actually kind of happening in this application. And so, this would be an allocation right here. So we got this malloc, right? So we got the buffer malloc, and we are allocating memory for a few things. This would be a great example of dynamic memory allocation. So this is, we're looking at some of the few pieces of this game which are done in Objective-C. And so this alloc init, well, alloc, that what that's doing is that's basically calling, it's hiding a call to this malloc over here, right? So we're doing some kind of memory allocation, right? And we're initializing this thing. Okay, so after we've allocated it, then we're going to initialize it. That's kind of something that Objective-C does. And Objective-C tries to kind of like wrap all of that into a single call. A lot of object-oriented languages do that. And then we do a similar thing here. And so these are every time we're making one of these things, we're allocating memory, right? And the only reason that we're not constant, because we call this redraw buffer a ton of times. So if I'm going at this Mac redraw buffer thing, okay, so that's actually never mind. We only call it once, so we're only allocating the memory for it once, and I think no. This is in the main game loop. So this is in that big infinite while loop that just keeps running. That's part of our game loop, which is remember, gather input, update the state of the world / entities, whatever stuff that represents the state of the game, and then draw a picture, right? So this is the drawing a picture part. This is the rendering the picture part to the screen. And what you'll notice is if we didn't wrap this in this at auto release pool thing here, which is like an Objective-C thing, basically what this auto release pool thing does, kind of behind the curtain, as it were, is it cleans up the memory that got allocated. So it just makes sure that after we do this particular kind of dynamic allocation here and here, that at the end of this thing, at the end of that logic, that whatever memory was allocated gets cleaned up. Which is why if you run the game kind of over a long period of time, you see that the memory usage never actually goes up. But notice how this particular, what I want to say is dynamic memory allocation is kind of baked into most object-oriented programming languages. It's more or less assumed that that's how you're going to do things, and a lot of people don't even know that there's a different way, that we don't necessarily have to do dynamic memory allocation. And in fact, there may actually be some pretty good reasons not to do dynamic memory allocation, particularly in a game, right? So maybe we don't necessarily. So Casey goes over some of the reasons why you don't want to do a dynamic memory allocation, and one of those reasons is just kind of, to my mind, very simple. It's we want to easily be able to reason about what our application does, right? And and what that means is we want to be able to know what are the failure points of the application, right? What are the pieces of logic such that when I run them, I might get a failure of the system that might be something that I might need to have the application respond to, right? And what are the places where I can more or less expect that logic that I run is always going to work no matter what, guaranteed 100% every time, bulletproof, solid, etc., right? And the problem with dynamic memory allocation is that every single time you do one of these, that's a failure point. Why? Well, because it's possible that the system, when I call this, or this, malloc or whatever, it's possible that the system doesn't have the memory that you want. And what does it do when it doesn't have the memory that you want? There's a lot of different sort of ways that this is kind of baked into object-oriented programming languages. As the memory pressure increases, or as your application starts to use up more memory than it should, usually what happens is you're given some kind of a memory warning, and then you're allowed to kind of clean things up. But that doesn't really address the actual point here, because the point is that right here at this point, in this place right where my cursor is, it's possible that running that command could result in a failure on some systems. Probably won't. And in fact, most of the strategy around memory allocation or handling memory is kind of waving our hands and kind of acting like the computer is this like abstract entity, right? That it doesn't exist in the physical world that you and I happen to exist in as flesh and blood, but rather that the computer is this like infinite memory machine, right? We just have all this memory available to us, and we kind of wave our hands and we sort of say, oh well, it probably won't it probably won't run out of memory. Okay. And what I can tell you from some professional experience working in some multimedia apps, it does in the wild run out of memory. So I've worked on some apps where we use some kind of a video playing framework that is heavily object oriented and uses quite a bit of dynamic memory allocation kind of in the background, and doesn't necessarily do such a great job of cleaning up all of that memory usage. And so over the course of using the app as somebody who's watching videos over the long term, eventually what happens is the amount of memory that they use gets leaked by the system over a long period of time, and there comes a point where the operating system steps in and kills the app. And how does that manifest itself? Well, to somebody using the app, it manifests itself as a crash, right? So you got your phone out, right? And by the way, these phones they're a very memory constrained device compared to, say, a full blown. I'm on my iMac here, right? And that's not a very memory constrained device at all, really. It's got loads of memory, right? And if I was building a custom gaming PC, that would have loads of memory. But a phone is very different. Those are fairly limited in terms of their memory capacity. And iPhone apps, which I work on day to day, it is not uncommon for them to just, especially if they're in kind of this like multimedia space where we're like downloading gobs of data from the internet or streaming or whatever, it's not uncommon for them to run out of memory, just flat out run out of memory, and have the operating system decide, you know what? iOS just says, okay, well, I've got this little box that you can run in, right? And if you're iPhone 6, whatever phone you are, I'm going to give you like a gig and a half, okay? And if you go over that gig, guess what? You're done. You're out. You're screwed. We're just going to crash you. Okay, and so I've worked on apps where I can go on to, we install this thing called Crashlytics. Basically, what it does is it monitors crashes. Okay, so monitors the crashes of the app. So you have like crashes caused by code, right? But you also have crashes caused by running out of memory, which is called an out-of-memory exception. And it was not uncommon for us to have something like 95% of app runs did not trigger an out-of-memory exception, but 5% did. Can you imagine 5% of the times that you're running an application, it just flat out like runs out of memory? So, I don't know, like, I will say this, okay? I'm not saying that you have to do it this way. I'm not saying that you have to do what Casey is doing, and I'm not saying that it's necessarily practical for plenty of organizations or for plenty of businesses, shall we say, to do it this, because there's a way of doing it that is opposite of this. That is saying, instead, here's what I'm going to do. I'm going to allocate all of the memory for the app/game up front completely, and it runs in this box of mine that I know about, okay? And there's no circumstance, if we were able to allocate all of that memory for that thing up front, right? And it just, then, and all of our code inside of that box is working as we would expect, then we can expect the app to just keep running indefinitely as long as there is power supplied to the computer, right? It will run indefinitely. It will never run out of memory because none of what we're doing is we have forced ourselves to run inside of a box of memory that we manage ourselves. We're not waving our hands about. We're not pretending that we live in this world where we have this like infinite amount of memory available to us and we can just allocate memory on the fly whenever we want. Because I've seen where that goes. I know what that is. I know what that world looks like. It looks like a Crashlytics where like 5% of your users are experiencing out of memory exceptions because we've decided that we don't care about memory and we're just gonna like wave our hands or just kind of say, well, they probably won't run out of memory, we don't know. Okay? All I'm saying is I'm not saying that you even necessarily have to not dynamically allocate memory. What I am saying is just this. It's just this. At the very least, know what you're doing. At the very least, know that you have decided to wave your hands about memory and not address it right now and not necessarily have a strategy or maybe even not necessarily know what how your app uses memory or how your game uses memory or what it's doing. That's all I'm saying. All I'm saying is at least understand what's going on here. At least understand that when you do something like this, when you dynamically allocate memory like this, that you're just kind of pretending that you live in this like infinite memory system and you just assume that the garbage collecting system is always going to clean things up for you, because it gets kind of messy if you think about it. If you think about having all of these entities that each have their own memory that the system is managing for you, and you're going to trust that it cleans out the memory for you. That's fine if you understand, like here I'm actually doing that, right? So I am actually using this object-oriented API right here, and I do understand that I'm dynamically allocating this memory, but I also understand that I need to clean it up, which is why I have this auto-release pool here. But a lot of what I see in mobile app development in particular is people just going and using someone's like third-party framework that does all this crap like under the scenes, and guess what? You just use someone's code, and now you don't know what it's doing with memory at all. You're kind of waving your hands about it, and you're saying that you're trusting that it's gonna manage memory for you correctly, and it's not gonna cause all those memory leaks and make it so that your app can't kind of continuously run. Okay, so all I'm saying is like you don't have to do one thing or the other, but you should know what you're doing. You should understand what it means to dynamically allocate memory. You should understand that this, technically speaking, is a possible failure point. And you do have to care about what happens if the system can't give you the memory that you're asking for, or if you exceed some limit beyond where the system sends you a message and says, hey, by the way, dude, like you're about to run out of memory. So at least understand what it means to be doing this. But for the purposes of this, wow, I actually did get off on a tangent. Oh, by the way, back to my Facebook interview. So in the process of that, I said it's garbage collected. I think what he wanted as an answer was like reference counting, because that's technically the way that Objective-C does it. And so I think he had like a little notepad in front of him. It was like, oh, well, he didn't say reference counting, so doesn't which I sort of consider like a reference counted environment to kind of be like garbage collecting. What it is, it's like you're allowing something to figure out what's pointing to what, and then it's going to go through and it's going to like sweep out the memory. But I guess I can sort of forgive Facebook. I mean, it was like a nice flight and some nice meals, and it was a nice hotel, that's for sure. So plus, like, I've got this interviewing series that I make money off of. So I guess it wasn't a total loss. Kind of interesting. Anyway, what we're gonna do is we are going to decide how to manage the game's state by statically allocating a large block of memory up front. And the first thing that we want to do is, remember, we're doing this kind of in a very bottom-up sort of a fashion. And by that, what I mean is, we're saying, okay, where are we in this game, this cross-platform game library? All right, and so what do we want to do here? It can be argued that we already have some game state. We've got this like local persists here, right? And that represents this kind of the state of the world, because if you think about it, the game library gets this input from the controllers, right? Gets a pointer to that input, and then what it does is it uses the controller input to then modify these local variables here. You know, the tone hertz, the offset x, offset y, those things. That's what it does, right? So these things are the state, because then that state, if we go down here to our render functions, that state then gets passed into the different rendering functions. So the offset x and offset y, that gets sent over to the render gradient function. And the game update sound, the tone hertz, gets sent over to that function. And so that's going to, you know, just based on the tone hertz, which is based on the controller, we modify the frequency of the sound that's playing. Okay. So what we want to do is we want to lift this state up into something that is more of the game's memory. So what we want to do is get to something that's more like a game memory, right? And that's going to have something in it. So I'm kind of cheating a little bit, because so we have permanent storage size. So there's going to be some, like, we're going to do kind of a partition of the memory. Watch the show and you'll see. So what we do is we take this giant glob of memory that represents the game state. We're partitioning it into two different areas. So we've got kind of more of the permanent game state, which is going to be like more of the like physicsy stuff. So where the player is, physics kind of, so like if they've got like a velocity vector or an acceleration vector, or maybe like a position where they are in like in a world, that would be kind of like the permanent storage. That's something where we need that to be reliable every frame, right? We need that to we need to be able to trust that. So that's kind of what that's for. And then we're just going to do a void star to the permanent storage. So that is just going to be this right here. This permanent storage is just that's just a chunk of memory right there. All right. And we got UN64 transient storage size, right? And then just a void star to the transient storage. Okay. And this transient storage is actually going to be much larger, because it's going to contain assets, that kind of stuff that kind of gets like streamed in as I actually am not far enough in the series to really be able to say much about how the transient storage is used, but I guess it's just important to note the difference between the two. So, and then you know, what I think we want to do as well is like take this other state down here and like move it into some other kind of a structure that kind of represents the state of the game. So we're going to do game state, okay, and we'll just lift that out, right? And you know, now that it's in here, it's not really going to be local persist. We don't need it to be local persist anymore, so we're just gonna have this as that structure. So offset and tone hertz. Oh, and another thing that's really important with this game memory is that we have some way of knowing if it was initialized, because on the first frame, what we're going to do is we're going to initialize all the value. Basically, we're going to take this game state and we're going to pretend that the start of the game memory, this permanent storage right here, we're going to pretend that that is the game state. Okay, so we're just kind of like, you can imagine that we're almost like overlaying this game state onto the top of that permanent storage. All right, and so we're going to, and that's how we're going to put some initial values in this game memory. So it's important to know that the game memory is initialized. So we're going to do that. So we're going to initialized. Okay, so we got these things, and now what we're going to do is, remember, this is quite different because this is where we're kind of drawing that line between the game and the platform layer. So remember that this is how we're envisioning what this is, because we're saying again that the game is a service that is provided to the platform. That's how that's sort of this like model of things that we made up to kind of reason about what's going on here. Okay, and so what we said is there's this platform, and every platform is going to talk to the game library, and the game library is going to provide services to it. So the platform is really responsible for allocating this giant blob of memory up front, and then what it's going to do is it's going to pass a pointer to the start of that memory to the game library, which will then use the memory to figure out, what kind of sound do I put out, what kind of picture am I going to draw. So we're going to do we're going to pass a pointer to the game memory, and that's just game memory star memory. Okay, and now that kind of gets us where we want to be with all of with game update and render. So that changes a little bit. But what we want to do, remember, we want to take the memory. So we say game state, right? Game state star, and we're going to just simply we're going to overlay that onto the beginning of the memory's permanent storage. If that makes sense, right? So the start of the memory's permanent storage is going to just be our game state, right? And then what we're going to do is we're going to say, okay, well, if we haven't really initialized the memory yet, then we need to initialize it, right? So this is where we'll do, so I'm just going to grab all the game state stuff, right? So this is where we're going to, set these to initial values, because now instead of these values being like a locally persisted variable that exists in this function or whatever, now we're calling them off the memory. We're calling them off the beginning of this game memory, right? So we just need to make sure that we initialize them from this game state pointer. And so that's 0, and then game state, the tone hertz. All right, I think we set that to like 256 to begin with, something like that. And then we just need to make sure that the memory, that we say, okay, well, now the memory is initialized, right? And what this does is, so on the first frame, since the memory is not going to be initialized, the reason that is set to false by default, so if we go over here, the reason that's set to false is because of the way that we allocate memory. We're actually going to allocate memory with mmap, and what that's going to do is it's going to put zeros in like every address. So it's going to be by default that's going to be set to false. So all those zeros are going to be false, and then so if it's not initialized, we're going to set all these variables on the game state, and then we're going to say the memory is initialized so that the next time we come through and make a frame, this is not that we're going to skip this logic. So we're only doing it once, right? So we don't want to call this on every frame, right? Because if we do, then we're not actually, then we're like overriding those variables every time. So now what I want to do is I just want to take this, because we've changed what offset X and tone hertz and all that stuff. Oops. No, it's not. So I wanted to do that, and so now you see that I'm just going through and making sure that we're calling all of these off of the game state and not off of anything else, right? So that's the idea, that they're no longer variables within the scope of this function, and so we're just gonna pass them in here instead, right? Okay, so that's good. That ought to work, and we've got kind of our, so at least in terms of how this is going to work in the cross-platform logic, I think we've got everything set up. And remember, all that we've done is we've said, okay, it's a little bit problematic that the offset X, offset Y, and tone hertz are just these like local variables inside of this function, right? And it's not really going to be manageable long term to just have all these like local persist variables there, and so kind of thinking a little bit ahead. We're gonna have to ask this question about how do we manage memory in the game, and so now we've kind of created this concept of a memory block and of game state that we're kind of like overlaying on top of that memory block. That's what we're doing here. So, going back to main, all right, so now we know that game update and render, okay, so game update and render, we know that we just changed this, right? And so we just changed this in a way that it now takes a pointer to this game memory struct. So again, bottom-up kind of thinking, or rather, compression-oriented programming, or whatever you want to call it. But the idea is that we allow kind of decisions at this at the individual feature level to sort of like propagate upwards throughout the rest of the system. And so now we know that we need a pointer to something that's a game memory struct. So we know that needs to exist somewhere, right? And so I'm going to go up to my main, and since we're probably not going to be creating that game memory structure, we don't want to be refreshing it every frame, so it needs to be before our run loop, and it needs to be before the frame counter, right? Because we don't want like this big allocation to affect our first frame count. So I would say probably like right here would be a good place to do something with memory, right? So right before we set up the controllers, maybe this is where we set up memory. We say, okay, game memory star. Oh wait, game memory star, game memory. And remember, that's just a struct, okay? So now we get into this question of, okay, so we've got this game memory star, right? So what do we want to do about that? Like, do we want to, so we probably want to have something kind of representing the number of, like the size of some of these things, right? So probably would want to, this can actually be kind of a cross-platform concept. And I'm actually going to go and nab that from my other layers, just to save a little bit of time. Okay. I want this here. So we have a way of kind of defining kilobytes and megabytes and gigabytes, and it's just through straight up text replacing, pound defines here. So if I do kilobytes of some amount, then I'm going to take that value and I multiply it times 1024, because a kilobyte is 1024 bytes, right? So value, I guess, is just Yeah, that's going to be in kilobytes. And of course, if I want to do megabytes, I just take the same value and I say, okay, well, that's kilobytes of that value times another 24. And similarly with gigabytes. This LL at the end, all that's doing is it's just casting it to an unsigned 64-bit integer. So just something to kind of note. So okay, well, so we got game memory dot. So we transient storage size, right? So that's going to be something like, I think what he does is like 64 megabytes, something like that. And then the permanent storage size is, I want to say it's like 4 gigabytes. Okay, and so that's a pretty large kind of thing. Yeah, you can just see the difference. We don't really need a lot of memory for the transient storage size. Another important thing to note is that like this can change. Like we're not making a big decision up front right here. We're not saying necessarily like, if we need more than that 64 megabytes to kind of represent sort of the state of physics and the player and like all that other stuff, we can change it. There's, we can make that a different thing. So, okay, those are our transient and permanent storage sizes. And another thing that is done, so we're going to use, in Handmade Hero uses virtual alloc, and I don't think that we have virtual alloc on Mac or on BSD. Rather, we have mmap, and that's pretty much. So if I look that up, let's look up, BSD mmap, and just see where we get with that. So I was looking at this earlier. Okay, this is free BSD. I imagine it's similar on a Mac. Okay, allocate memory or map files or devices into memory, blah, 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 standard C library. System calls the pages starting at address and continuing for the most length of bytes. Okay, so we care about this, right? This thing here. And I'm kind of cheating because, again, I've done all this work ahead of time, so in order to be able to talk about it. So I just copied that in. All right, so, and then mmap, remember that returns a void star. And so if I'm thinking about this, I've got my game memory, right? Dot permanent storage, right? So permanent storage, and then that's going to be mmap of, oops, that's not what I wanted. I love Vim, just like press a key and all of a sudden, okay, so we don't want that, so that's mmap. All right, so what's this void star address? Okay, and one of the things that's kind of important to note is one of the things that's done in Handmade Hero is we decide that if this is an internal build for the purpose of testing. Well, first of all, actually, let's get at like what is this void star address? So that's the base address of where this memory is going to live. Okay, and so this is kind of an interesting thing. There are some interesting things that we can do. So one of the things that we can do, we can decide to say, okay, well, I don't necessarily care where the base address of this memory is. And what I'm going to do is, because there are certain things where we don't need to care. So we don't really care where the sound buffer is. We don't really care where the display buffer is. Right, so there are parts of this where we don't necessarily care where that memory lives, and in fact, if we look at the documentation, like let's look at void star address for the address, starting at address and continuing for at most length bytes to be mapped from the object described by the file descriptor. So that's if we want to do like memory mapped file I/O, starting at a byte offset. Okay, there's something that says if the address, yeah, okay, so if address is non-zero, it is used as a hint to the system. as a convenience to the system, the actual address may, okay, well. If address is 0, an address will be selected by the system. Okay, so what is this saying? What that's saying is, if we pass 0 in here, we're saying, hey operating, hey BSD, like you go and you figure out where this is going to go, and we don't really care, right? But if we do actually pass a pointer to like a starting address, then we're saying, hey, we want this to live in a certain place in memory. We actually kind of want to know where it is. And in some circumstances, we can actually do that, and there might be some benefits in doing that. One of the benefits of doing that, of knowing where the starting address is we can, you saw it in a few episodes prior to this. What we can actually do is we can know, we can do like a kind of a hot loading system where we've got the game running and we make some changes to the code while the game's running, and then we just rebuild the game library and then reload it, because this memory was still at the same address, right? Since we didn't change like where the base address of that memory is, that game library can change while it's running, and we can see all kinds of we don't have to like lose our progress in the game or anything like that, and we can do this like really cool kind of hot loading feature, because we haven't changed where the game memory, because remember it's passing a pointer to where the start of the game memory is, and if that location changes for some reason, then the game library won't know necessarily what the state is or anything like that. So this is pretty cool if we can actually control what that is. So if we can control what the base address is, we can do things like hot loading. Another cool feature that you'll see pretty soon is the ability to record your inputs from the controller as you're playing, and then your character goes in different parts of the screen or whatever, and then you can replay that over and over again. Another reason that you can do that is because we're going to set this up so that we know where the base address for our game memory is, and then we rebuild that library and just reload the library using the exact same memory. Like, that never changed. The memory never got overwritten or moved to a different place. It's the same memory because we know where it starts in the system. So there's some pretty cool stuff that you can do by kind of getting in there, and manually managing some of this. So in order to do that, first thing we need to do is we're going to say, okay, well, we actually need to modify the build system. So first of all, we're not always going to be able to guarantee that we can get the location in memory that we want. So we need to have kind of a concept of what's an internal build and what is what's not an internal build. And so we're just going to use like an if kind of thing. So if we go handmade internal, okay, then we're gonna know what the base address is, and then we're gonna say, okay, else, do something else, and if. Okay, so if it's an internal build, then what we're gonna do is we're gonna go, okay, so then void star base address, right? And what we can actually do is we can say just offset this by 8 GB in the system, okay? And so what this does is it just sets a base address. It's like 8 gigs up, right? And so most, this is kind of like system dependent. You might not be able to you might not necessarily even have those 8 gigs where you could offset that, and that's fine. I happen to know that I can on this Mac because it's got a lot of memory, etc. So it might be different for your system. Else, void star base address just 0, right? Because if we pass 0 into this thing, then if we pass 0 into it, we're basically saying operating system, you figure out where that goes. And we would do this in a production build of the game, because a production build of the game is not something where we're going to be hot loading the game library or anything like that. That's something where we've shipped the game and we're saying, okay, the game's done, we're not working on it anymore. Have fun, go play, right? So that's where we're just saying, okay, on that circumstance in our shipping build, we would want to say, yeah, just whatever address you want, right? So that's that. Now, what we want to do is we need to modify our build script. So this is the build script, and all we're doing here is we're just adding that flag. I actually think it's just -d handmade internal equals 1. And so right now what we're saying is that while we're kind of in a development mode, we are going to just have this, like we're going to set this flag to 1 so that we can guarantee that it's allocated at a certain address. Okay. And actually what I want to make sure is I want to make sure that that's a game memory. I want to make sure that I got that right, because I may not have. All right. No, yeah, it is -d. Yeah, for both. This is kind of cool too. So one of the things you'll note too is, like, if you're actually, I don't want to segue too much because I've been talking a lot, but if you do like a lot of iOS development or like that kind of thing, you'll notice that just being able to put these into your project is this like massively confusing thing. It's like you have to like figure out where in the Xcode project it goes. But when you actually roll your own build system, like I know procedurally what is happening here. And I know that that is an argument that needs to be passed on this compile line. And I know kind of like what the order is. And so I just put it there, right? So like, I don't have to go through this like, complicated build system that someone already set up for me that I don't know what all the parts are and like figure out where that goes. I can just put things here, which is pretty cool. So, so we got that. So we got our base address, 8 gigabytes, otherwise 0. And then the size of this thing is, I believe that's just the permanent storage size. Or no, yeah, permanent storage. Actually, I'm going to move that up over. Okay. So that's just game memory.permanent storage size, right? Okay. These are the protection flags, and I believe that they're the same. So hang on, I want to make sure I got that right. So I'm gonna go back. And I think that it's just read and write. So I'm pretty confident that that's the case. So go down. Yeah. Okay, so we did this. All right, I guess I had things a little bit different here, but these are our access flags, right? Oh yeah, okay. So we do want to change the base address to, okay. So our access flags, right? That just is just saying like, what can we do with this memory? We want protected read and protected write. So we're just going to use access flags here, right? And another thing too is, I guess we're using like a char star. Did I say void? I forget. Hang on just a second. I'm not entirely sure why this is a char star. No, oh yeah, maybe that's so that we can know if we cast it to a char star, that will tell it, because I think that's like it's like an 8 bits. So it's just saying like, with an 8-bit offset, go this far. I want to say that's what that is. So that's why we need to do a char star there. Okay. And so those are our access flags. Those are going to be the same. And then allocation flags are going to be a little bit different depending on if we're starting with our own base address. So we're going to do allocation flags. And I got to remember, what did I do here? Private, anonymous, and fixed. Okay, yeah, so I think allocation flags, you have to tell it, that's another thing too, is you have to tell it that you're doing fixed allocation. So let's see where we find that. Remember all this stuff, since there's like very little in the way of tutorials that are on any of this stuff, it took me a while to like just straight up do the searching for it. But so map fixed does not permit the system to select a different address than the one specified. So this is what we want. We want to know what the base address of this memory is. If the specified address cannot be used, mmap will fail. If map fixed, the specified adder must be a multiple of the page size. Okay, which I think is, 8 gigabytes is probably a multiple of the page size. Like what, 64? I forget exactly what I think the default page size is like 64 kilobytes. I could be wrong. If map XL is not specified, no, replaces any previous mappings in the address from adder plus. Okay. So yeah, I think we want map fixed. Map anonymous memory is not associated with any specific file. So that's why we chose map anon here. We want anonymous. We're not actually doing memory map file. We're not like picking a file that the virtual memory system is going to map this memory to, although we can, and later on we actually do, which is pretty cool because if you we'll get to it, but the way that you do the looped editing where you can replay the memory back is you actually you memory map that. You map the memory to a file, and then you have it like load that file, and you can like actually have it load like multiple, this stuff is so cool. You can actually have it load multiple replays. So like if you wanted to, what you could do is you could say, okay, well this is my like first replay, I'm gonna do it there. Or like, have like my 5th replay and I can like load from that file if I want to. So imagine that you're kind of playing a game and you get to some level and you're like, I wanna record that and like maybe later on while I'm editing this game, I can play that progress back and just kind of see that on loop, or stop there and start controlling the game, etc. Having a memory mapped file that contains all of this memory block in that file is really freaking useful. It's cool. So anyway, kind of just explaining some of these things as we go through. And then map private, that's got to be in here somewhere. Modifications are private. Yeah, I mean, I think that's what we care about. So again, this is this is FreeBSD. I think I don't know enough about my OS history, but I want to. So I know that Mac OS, the modern version, from like OS 10 forward, is based off of BSD, and so I think you can pretty much use like the BSD documentation here to kind of represent what you want. So so far I've had no problem with it. I've been able to just use BSD. So I'm going to take that, and then we want to do something else if it's not an internal build. So on a production build, the only difference, so we're going to do anonymous, private, but we're not going to do fixed. Remember, because we said we want the operating system on a production build to just pick a base address for us, right? Okay, so we've got, and then these are our allocation flags, right? So allocation flags. And then the file descriptor, I want to say if we don't, so FD is, you'll see this is kind of a thing that pops up in BSD a lot as well. File descriptor, we would use that to, when we do like file I/O, we would use a file descriptor to it's like a whole other structure or like a whole other thing you set up that, well, the system gives you a file descriptor. It's a complicated thing. But if we wanted to, like, get some stuff from the file system, we would use a file descriptor. But we're not going to use one because, remember, we're not doing memory mapped file I/O. We're just doing like a block of memory. So we're not going to do anything with this file descriptor. And in fact, if we read the documentation for mmap, I think it will actually tell us that file descriptor is like, we set it to like -1 or something if we don't use it. I forget. I have the right thing somewhere. I'll just reference my other layer here. Yeah, so we pass -1 if we're not going to do anything with it, and then we pass 0 if we're going to do something with it. Oh, we also want to calculate the total size, so we're going to grab that here. So that's the total size. And yeah, so this file descriptor, not going to do anything with it, so we're going to say -1 and then no offset. I forget what this offset parameter is, or what the deal is with that. Offset FD references a regular file, the range of the bytes starting at offset. Okay, so offset would be like an offset, some kind of byte offset into a memory map file. We're passing 0 because we're not doing memory mapped file I/O. Okay, so remember, every time you allocate memory, you introduce a possible failure point into your application. So this can fail, and it's important that we recognize that. So we're trying to allocate 64 megabytes. It's possible that that fails. And so we want to make sure that we handle that. And in this case, all I'm doing is I'm just saying, okay, well, let's just trigger an exception. So if the permanent storage, we weren't able to map it, we failed for some reason, I'm going to print something, and then we're just going to raise an exception. Okay, so that's fine. Now, all we need to do is map the transient storage, right? So I'm actually just going to grab that, grab all of this, and walk through it a little bit. So again, we're using, I suppose we could have used a char star here, but the idea is it's 8 bits is kind of the increment in memory that we want to move across. And so we're saying this transient storage, we're just going to take the start of the permanent storage, right, interpret it as like 8 bits, right? And then we're just going to, do some pointer arithmetic on that. And we're going to add the size of that as bytes, right? Oh, okay, so this is just saying like bytes, because remember, if we do like an unsigned 8-bit integer star, that's like 1 byte, because 8 bits is a byte. So permanent storage size is in bytes, and so we're saying like give us a byte pointer, right? Give us a byte pointer. And we're going to offset that by the amount of bytes that are in the permanent storage, which is 4 gigabytes, right? So this is in bytes as well, and that's in a 60. The reason that that's in the byte number is in a 64 bit value is because if it's smaller than that, then a very large number could possibly overflow. So if we did that like in 16 bits or something, that would overflow, or like 32 would overflow. So we do it in bytes because we do the largest possible, we do 64 bits because we could store a very large number in there without overflowing. That's the thinking. Okay, so that's where this base address starts. And remember that if we had done that, okay, so remember this is starting at the permanent storage, wherever that was allocated. If we're doing an internal build, we're mapping this in a fixed way, so we know exactly where it's allocated. It's allocated like 8 gigabytes up from wherever the base of memory is, right? But if we're doing a production build, a shipping build, then we're going to say we're just going to let the operating system tell us where that's going to be, right? And so when we do this, when we do this mmap, that returns a void star pointer, okay? And so then that pointer tells us where that is in memory. And all we're doing is we're saying start at that void star pointer, interpret it as if it's, a byte pointer, and then add however many bytes, and that's going to be our offset into wherever the permanent storage is. So, and the idea is that they kind of occur right after one another, right? And so then we, when we're done with that, we're going to say, okay, well, if we failed to map the transient storage, the 4 gigabytes that this game represents, then we flat out crash. Okay, and so this is, gosh, like we're going an hour or so, and I feel like I've talked a lot, but this is sort of like it sort of gets into like one of the things that annoys me about kind of like modern programming, or the way that it's done in a lot of these so I write a lot of Swift, and I think that there are a lot of really cool language constructs and concepts that are pretty useful in Swift. One of them is the optional. Okay, and so the optional is this idea of, we're going to kind of more formally codify what it means for something to have a value or not. We're going to make that like a part of the language. Okay, that's kind of the idea. And a lot of this, like it actually comes from pointers, right? Because like a pointer can possibly, this it's possible that this void star, for example, like this base address, it's possible that points to nothing. It's possible that it points to nil, right? Which would mean like we're going to interpret that as no value. Well, oftentimes what I see in a lot of iOS applications, especially when it comes to optionals, is there's like a lot of there's like a ton of hand waving about, oh well, do we have a value or not? I'm not really sure. I don't know. Just don't do anything if we don't have a value. I don't know. I'm scared. I don't know what to do. And so you'll see if you write Swift or whatever, there's like a lot of question mark, and it's like it bothers me, and it bothers me. I'm not necessarily opposed to having a silent failure when you don't have something that you need. There are circumstances where that's okay. And in fact, you probably don't want the app to crash in those circumstances, at least not in a production build. What bothers me though is how it can kind of ruin understanding the actual control flow of the application, and how it can make an app that would have otherwise been simple and straightforward and easy to follow something where there's like all these like failure points riddled throughout the application. Oh, we might not have a value there. That could fail. Oh, and maybe we don't have a value there. Oh, that could fail. And like, oh, that could fail too. What do we do? And oftentimes, optionals are actually used as like this. Like they're used because we know that the operating system, or we trust that I'm sorry, I'm going on a bit of a tangent on iOS development, but because a lot of times optionals are used because, say we're going to hook up some UI or like a label or a button or something, and we're trusting that the software kit, the UI kit, is going to hook that up for us. And so one of the funny requirements of Swift is like it tells you, hey, like anytime that you say like a variable is a property of something, you need to give it an initialized value or give it an initializer. Otherwise, you have to say that that's an optional, because optionals are the only way that you can say something is nil or not, or like might not have a value. Well, it's really weird because you have these bits of the user interface that you know for sure are going to be hooked up by the time that you use them. And so really, but you have to express those things as an optional. You have to express them as saying, I don't know if we have this or not, right? And it's like, we're talking about like a label or a button or something where it's like, that that the UI kit's going to hook that thing up, right? And we should be able to easily reason about these things, right? And it should be that when I get to the part in the code where I know that I need that thing, I should be able to just say, here's my label, right? Like I don't have to unwrap it. I don't have to silently fail. It's like, here's my label. And oftentimes when I write Swift code, what I do is I say, you know what? Right here, I am expecting that user interface kit has hooked up my button or my label or my thing, and I'm going to explicitly crash if it didn't do that, because that is an absolute base assumption. Maybe somebody forgot to hook it up in interface builder or something, right? But the point is that I think it's important that we be able to simply and clearly and directly reason about the programs that we make. And what I think is really, I kind of want to stop for a moment and say what's really cool about this system right here. What I really like about it is we are doing that. We are saying, here's a container for the entire application. This is all of the memory that the game is going to run in. You either have that right away at startup and you're going to run forever, or you don't and you crash right away. And we have an app that once you're in the box and you're running, instead of, well, I kind of got into the box and the box is dimpled with all of these possible places where we could fail and we might not fail, and we just sort of like throw our hands up if we can't handle one of these allocations, or we can't handle this optional that doesn't have a value. I think it's better to, instead of having an application that's got multiple complicated failure points riddled all over the place, I think it's better to sort of define a wall beyond which everything else is expected to run. That's the idea. We say, starting at the very beginning of the application, these are the possible failure points that we could have on this system. We might fail on this system because we don't have memory, right? We might fail because we didn't allocate all the memory. But after that point, we're not going to have any issues with memory, because we allocated it, we know we got it, and we can safely reason simply about what our application does after that point. And I want to say the same thing about optionals. In modern Swift applications, you should try to define a wall beyond which things can't be optional. Say if we're doing networking, we might get some stuff back from the server. We might not. So what do? We say, okay, we're getting data from the server. Here's where we draw that line. We say, we may or may not get stuff. And then we're going to take all this possible optional stuff and we're going to cast it over to non-optional, simple, direct variables that we can reason about. And everything over here is a space that we understand that doesn't have failure points. If this code runs, it's not going to crash. If it runs, it's not going to silently fail. We can reason about it clearly, simply, directly. Rant over. That's what I like about this. You can obviously program in any way you want, but I think it's much easier to be more of an engineer and clearly define where you know something can or can't fail up front and force that decision so that you can have a much larger space later on that represents all of the places that represents non-failure, that represents expected behavior, clear reasoning, simple, direct logic. And we've done that with this. We've done that at least with memory allocation. Okay, so now we've got the memory, we've got that all going, we've got, I suppose we just try and like build it. So let's do that. Where am I? Okay, So I need to go day 17, handmade code. I know. So what is it? It's like a Saturday morning, and here I am like ranting about, not being able to reason about memory. Okay, so all right, so looks like there was something game memory. Okay, 14. Wait, what? Hang on. Oh, that was in file included. Okay, so handmade. I probably forgot a semicolon or something silly. Handmade CPP, probably in my game memory struct somewhere, I'm guessing. Wait, 14 it said? I'm confused. In file included, handmade. 141, gotcha. No. Sorry, my rant has, oh, game state. I didn't put a semicolon at the end of game state. Okay. My rant has greatly diminished my ability to write code. And then game memory, 467 on our platform layer code. Oh yeah, that's right. It's not a star, it's just a straight up struct. Okay. So we got that. And it builds. It builds, but does it run? So we've got, let's see. Day 17. And it crashes. Pretty much immediately. Permanent storage not allocated. Failed to allocate permanent storage. Cool. So this is great because now we know, sort of what. So why did we fail to allocate permanent storage? That's a great question. Because this isn't happening in my other one. Oh, wait, what? Oh, okay. I don't know why I did that. Duh. If I'm going to go through all of the effort of defining a base address, I should probably put the base address in there. So that's fantastic. All right. So rebuild and let's run it. Okay. Okay, and so remember, yes, the app, the game does everything that it still did, right? So we know that it works, but there's maybe some other things that we care about. And gosh, where are we coming up on time here? I've been ranting and raving for like an hour and 15 minutes. So I recommend this YouTube channel. It's Isaac Arthur. He does these like amazing like really like kind of long form talks about colonizing the stars and like building Dyson spheres and all this other cool stuff. Yeah, I like how he starts every single episode. He's like, "It's going to be a while. You may want to get a drink and a snack." Okay, so right, so we care about memory, and so notice this still says 22.2 megabytes, but it looks like it's got a larger virtual memory size, and there's other things that we can kind of know about. So we could actually reason about. God, that's annoying. We could reason about making sure that we got our base address. So I'm going to spend a little bit. I'm going to spend a little bit of time on that because I think it's going to be valuable. So, and every time I do this, I have to change where the executable goes. So I'm going to edit this and change it to the executable for day. So where are we now? Day 17 for me. Oops. Okay, there we go. All right. So yeah, so we got all this stuff going, and what I want to do is just maybe try and reason a little bit about, if we can, reason about making sure that we got what we wanted out of our memory here. So is this even like, I feel like the code did change. Okay, here we go. So this is what we wanted. So I'm just gonna like put a breakpoint here. I just want to like walk through the debugger and see that we got kind of what we wanted. So that's the hope. All right. So this breakpoint's there, and I'm looking at so my game memory struct. I've got permanent storage size. Looks like, is that 64 megabytes? I don't know. Let's find out. I will bring up a spreadsheet because I don't like calculators because they often get things wrong. And so I'm gonna make a spreadsheet. Also, how I do my taxes. So our base number is this, divided by 1024 gives us the number of kilobytes. No, that's so megabyte. No, this is bytes. This would give us kilobytes, and then this thing divided by another 1024 would give us megabytes. Oh wait, 4096. I probably got this wrong. This seemed big. Wait a second. Gigabytes. Well, you do see this, address-wise. So it looks like we do have a kind of like. Okay, so one really quick thing to guess. What I want to see is every time we run this, do we get the same base address? Right. So we're gonna run, and look, yeah. So, and the same offset every time. So that's kind of the only like big thing that really matters. I don't know why this. Oh, well, that is probably bad. Okay, so I realize that we do have a bug here, or at least, well, not necessarily a bug, but something that we don't want. Yeah, we want the transient. We want the transient to be 4 gigabytes, and the then we want the permanent to be 64 megabytes. I was like, wait a second, this is silly. That doesn't make much sense. So yeah, let's redo that. Okay, let's rebuild. Okay, so we got that. All right, so we're gonna run again. All right, now, yeah, I knew that was wrong. Okay, so this number here, I'm gonna plug that in. That's gotta give us like, oh, come on. There we go, copy that. I'm gonna put that into my magical spreadsheet. 64, okay, so that's 64 megabytes. All right, and then 4096 megabytes would be 4 gigabytes. So that's what we calculated earlier, so that's right. Okay, and so then again, notice that this permanent storage, the base address, is the same. It's been the same as every time that we've run this. So we are in fact kind of getting what we wanted out of this memory map BSD function, right? And now we got this transient storage size, which is like, that's our 4 gigabytes. And then the transient storage. So that looks like, I mean, yeah, it looks like it's starting, 4 gigabytes further ahead than where this permanent storage location is. And remember, virtual memory is, it's much more vast than So these are like virtual addresses. They're not necessarily like real memory. They're not necessarily physical memory addresses, because the virtual memory system, like, it also uses files, and it can use file space in addition to real physical memory space. Virtual memory being like, hey, this is kind of like a made up memory address system that we're using because we want to make it so that it's possible to run very large memory programs even when you may not necessarily have that amount of physical memory on hand. So that's why these addresses are so large. Um, Bit of a caveat, or a bit of a thing to kind of point out. So that's that. But yeah, I mean, overall, I think we're getting what we want here. So I'm gonna rerun and just make sure. Yeah, and every time these are exactly the same. So that is the result that we want. And the reason that we want that result is so that we can. Well, there's a lot of there's a lot of reasons why we did memory this way, but this will allow us to do this really cool kind of hot loading feature that you're just it's kind of funny. One of the things kind of Casey points out is like, there was actually an entire startup built around this idea of like live loop editing your gameplay as so like recording your gameplay and then like replaying it. And I don't, to my knowledge, I don't know that this is available in like Unity or Unreal or any of the major like engines that you can go and use. I could be wrong. I sort of don't pay attention to any of that stuff because I don't care, and I don't want to spend money because I'm cheap and very frugal and like working on being financially independent. So that's that. But largely, like, yeah. So it's this what I'm trying to impress upon you, and also what Casey is has said on numerous occasions, is like, we make a big deal out of these things that if we just started at a low enough level where we had enough control over what's going on, you realize that these big features are actually not that hard to do. It's like, how much time did we spend here? We spent like an hour and a half, and all we decided was we're gonna make some decisions up front about how memory gets used. That we're not just gonna like wave our hands and like turn the game into this like allocation festival and like willy-nilly allocate all over the place. So when you make certain kinds of decisions early on, in terms of how where the failure points of your application or your game reside, then you can do some pretty amazing things, and you're going to see that. So I encourage you to kind of keep following along. On the next episode, we are going to do. We're actually going to do file I/O from the platform layer. I know I said yesterday that we are going to do it, but then I actually looked at the order of things, and memory was kind of next on the agenda, so we did memory instead. But yeah, all the source code that we've gone over is available. I've got the platform layer that's like following the videos, and then I've also got the platform layer that's not following the videos. And I'm going to say this again before I'm out of breath, but go and buy a copy of Handmade Hero. It's absolutely worth the money. $15, you're going to learn a lot. You can also support me on Patreon. Subscribe. I really appreciate it. I'm not doing any like fancy promotion-y stuff. All of this has been for free in my spare time, teaching you how to make a game engine from scratch. So if you do support me, obviously just, hey, send me a message and like let me know if there's any questions that you have, or if there's anything that you would like me to cover, and I will discuss it in one of these episodes. So with that said, rant aside, I had a very ranty Saturday morning, but that aside, enjoy your weekend. It's beautiful. I think I'm going to go skiing tomorrow. So, yeah, have a good time. I'll see you guys later.